So hi, welcome to a special edition of Trends in AI. My name is Jakub Savrel, and today I have the pleasure to have as a guest Sara Hooker, who's had a distinguished research career in many places, but is currently the head of Cohere For AI, which is a little bit of a different twist on the usual corporate research lab. On your homepage, I read that you are a fundamental research lab. So I'm very curious about that. So maybe before we dive into that, can you tell us a little bit about your background and kind of what got you fascinated in working on AI and machine learning and large language models, and how that path led you to Cohere For AI?
Yeah, so it's lovely to be here. Thank you for the invitation. So, as you mentioned, I'm currently leading Cohere For AI. So, it's a fundamental research lab, but it's also focused on creating more entry points into machine learning. And in many ways, it's the lab that I wish it existed when I first started research. I think my career has been somewhat eccentric. I would call it a little bit rogue. Like a lot of how my career has developed is by just working on problems that I find interesting. So I initially started as an economist, and I was working on, at the time, antitrust cases. So working on really interesting problems where essentially you're trying to introduce a lot of assumptions to make a linear model fit. And I think a lot of what first got me interested in both the research that led me to Google Brain, as well as the research I'm currently doing at Cohere For AI, or supporting at Cohere For AI, is this idea that the world is more complex. So maybe our economists tend to really love linear models. But as we all know, sometimes these assumptions about distributions are violated. So when I first moved to the Bay Area, I felt like there was so much exposure to really talking to engineers and researchers who were modeling the world in more complex ways. And I feel like that was a definitive turning point. It was almost the beginning of what I would call the brute force approach. I felt like I had to learn more. So I joined a startup called Udemy at the time, and I was working on recommendation algorithms and fraud detection, but I also started teaching machine learning. So around the same time, I started both teaching as well as developing a curriculum. And then after that, I joined Brain. So I was at Brain for the last 5 years before I came and started a Cohere For AI. And a lot of what I was working on at Brain was how do we train models to fulfill multiple criteria. So maybe we don't just want high performance, but we want models that are more efficient or show robustness to certain environments or distribution shifts. And most recently, a lot of my work has been about the trade-offs between each of these. So when you have multiple desirable criteria, do they trade off? So privacy and compression, or robustness and compression. But in general, I would say one of the questions I'm most interested in is, why do we need such large models to begin with?
Right.
You asked me.
Why not linear regression? Kind of going back
Yeah.
to the roots.
Well, I'm not going to defend linear regression, but there is like this really interesting question of why we're scaling so quickly. Can we do more with less? So what are these extra weights giving us? So when you first posed this question, you were asking about, how did I get to large language models? I actually think a lot of my interest is in how do we deliver some of this progress that large language models have unlocked in a way in which requires resources. And I think a lot of what is maybe the final thing I'll mention about this path is that along the way, it's become just as important to me, not just what questions we work on, but how research is done. I think there's been a fundamental shift. You introduced Cohere For AI as maybe a different type of industry lab. I think, first of all, it's just truly exciting that we're in an era where progress doesn't just happen in small academic labs. There's more spaces in which we can work on research. So this is in some ways a fairly radical shift. Like until the 19th century, everyone was an independent researcher. And then after that, we had the kind of professionalization or industrialization of research in the sense that you had to be affiliated with a society or group. And now we see two things. We see more spaces in which research can be done and people are open sourcing knowledge, but also we see more community-driven research. And that's kind of exciting for a different reason, because it's fundamentally a different way of producing knowledge than all the waves that have come before it. So for me, this is also exciting. It's not just what we work on, but how do we create new ways of collaboration where we're empowering these new entry points and new ways of doing research that didn't exist before?
So what are some of the topics that are, you just guys have just started the lab, right? So it's kind of still greenfielding, probably a lot of research. What are some of the topics that you guys are planning to do work on?
I really want to facilitate and support researchers who want to work in this context of large language models. And in particular, there is this really important question of ML efficiency. So how can we make progress on achieving similar performance gains at far less complexity? But also there's other topics, like a lot of my research has been in trustworthy ML. So how do we guarantee reliability and ensure that our models are performing the way that we expect them to? The truth about curiosity-driven research is that a lot of it's coming from the community. So the community will bubble up an idea and will try and facilitate in different ways. So some of my core research agenda is actually still multi-institutional collaborations that are centered on things like hardware algorithm compatibility. So this is another really interesting area where a lot of my research, kind of my grumpy paper, the hardware lottery, was about, which is how can we do better at different levels of the stack? So, we have hardware, we have software, we have algorithms. Right now, we almost treat these as fairly siloed, and where we do have co-design, often at certain biases, so preferences for one algorithm over another. So a lot of my work recently has been, let's have cross-disciplinary collaborations, and let's bring in hardware specialists and really think about how we both design new algorithms, like, for example, mixture of experts is a good example where there's still a lot of optimization there about how you actually deploy these models in practice. And a lot of it is hardware design and co-design capabilities.
I read that the new NVIDIA chip is actually kind of super optimized for transformers. So we're never going to get rid of them again.
Yeah, and I think this is just, it's kind of amplifying a trend which has existed for a while, but it is very precarious because it means that when we're betting heavier and heavier on like certain types of algorithms succeeding, which means that the next transformer, whatever that is, may have a hard time emerging as the next transformer.
Right. For our audience, Sara wrote a great paper, The Hardware Lottery, which kind of started discussion in this direction. Very recommendable read. So yeah, you mentioned language models, large language models as being kind of a focus point. It also makes sense because Cohere as a company kind of has this as a product, right? Large language models as a service. How do you see the development of that subdiscipline? I mean, is it just about large? Is it, like retrieval augmented, more efficient? What do you see as kind of interesting papers or topics that have recently come up in that area? And most of all, is it just going to be language models, or is everything going multimodal in the next year or so?
Yeah, I think it's really interesting. So the reason why I'm excited to support research collaborations which work on this context is I think as a research lab, you always have to think through, well, what is unique about our setting in terms of offering something to the ecosystem of research? And I think that there's very few places in the world you can currently study large language models. But that being said, like, our community does research across the gamut. So I think we have a lot of reinforcement learning researchers, we have computer vision, and we have a lot of projects emerging around those topics. But I think your wider question is, well, what's interesting right now? And even in terms of, you mentioned retrieval, I would put that under what is interesting in terms of how we make these a little bit more efficient. So I guess there's a few things. So one is retrieval is interesting because it's an architectural innovation, which is fairly cheap. So it's costing you storage in terms of memory for your database, but in some ways it's really improving the performance of your model in terms of minimizing the number of parameters, and you can do it in all these clever ways. So I think that's very exciting. I actually think there's a lot of research right now on how to make better retro type models. I would say the other axis, which I find very compelling right now, is if we care more about the data space, can we get away with much more efficient models? And I think here there's very promising signal that because we've abstracted away the data space for so long, we said we're going to focus on essentially building bigger and bigger representations with the trust that we can delegate to the model the representation and it will improve performance. But often when you particularly have large web crawl databases, or you have a lack of a human curation on your data set, you may be regularizing a lot of your model capacity by not caring about your data space, by not focusing on what is higher quality data. And I think to a large extent, a lot of our scaling laws can be explained by the fact that we've ignored the data pipeline completely. So Chinchilla is a first signal in this regard. So Chinchilla is showing you can really reduce the parameters if you increase both the quantity and perhaps the quality, although it's very ambiguous there what they actually did. So not quite, can't precisely say there. But I think my hypothesis is a little bit even stricter. I think having a good estimate of data quality and data instance quality, we may be able to get away even for the same data quantity with less parameter size. And so I think that's a really interesting hypothesis to explore. And I feel like it's a very timely question, which is by caring again about the data space, can we do better? The difficult thing is, how do you estimate data quality at scale? So many of our data cleaning processes at this scale have amounted to rule-based filters. So drop anything with less than 3 Reddit comment replies. Like, they're pretty crude filters. But to score data instances for quality, it requires something that's a very cheap proxy. So how do we do that? It becomes like a big question of interest. So I think that's the second direction. These are, in some ways, those amount to pre-training questions. So things that I think are quite compelling in the pre-training space. There's a whole separate set of questions about how do we do fine-tuning better? So how do we do this transfer space better? And that is, so if you think about where your computational cost is in a model, in terms of a scalable production scale model, a lot of it's actually in your inference space, because you're leveraging the same model again and again, but it's also in your fine-tuning space. So how do you fine-tune? So for me, a lot of the most compelling efficiency questions, if you were to think about the ML workload, it's estimated 70% is in this inference or fine-tuning part of the machine learning workload versus the training, even as we scale further and further. So both matter. And I think that it's interesting to think about how can we do better at the fine-tuning. And that includes directions like partial updates, adapter strategies. And the difficulty with adapters is that they actually add memory requirements because you're adding parameters. But if you can do that in a more simple way, so by example, streaming weights, there's strategies there that require both hardware and algorithm co-optimization. So this is what makes it tricky. So I'll pause there.
Those are some very cool directions to of future work. What about multimodal? Do you
Oh, yeah.
Plan to also dive into that? Are language models which are not multimodal still going to be around?
So I think this is actually a fascinating question. It's worthwhile placing it in history. So up until very recently, we almost treated these subfields in siloed ways. So we had vision, we had audio, we had text, but these were all treated
Pretty
with
much
its own
broken
body
down
of
this year, right?
Yeah. And it's very important to understand why multimodal matters, but also why it started to break down this year. So like, one is, we inherently as humans rely on multimodal signals. So for our sensory inputs and decision making is multimodal in the sense that I'm speaking to you, you're seeing me. We also have touch and motion, which, by the way, I think is completely motion as a signal is so important for us humans, and I think is one of the trickiest things to try and capture in our current framework, because motion allows us to calibrate our uncertainty. If we don't quite see something, we can move forward in space and recalibrate.
Active perception in that sense.
Yes, 100%. So these are all very critical, and they're all synchronized. So you are hearing me and seeing me at the same time, despite in practice there being a latency. So our brain waits for everything, synchronizes it, and then makes a decision. So to treat them as siloed until now was a naive modeling assumption, but a necessary one, because we didn't have the compute necessary to model these representations. Frankly, I think compute is still a huge issue in multimodal, because in many ways, algorithms are very inefficient. It requires a lot of parameters to try and arrive at a useful representation. So there, algorithm design is going to matter more and more. But in general, this is a super exciting chapter that's being unblocked, and it feels like it naturally adds a more nuanced way to navigate the world, because we now have different sources of information that we're combining in unique ways.
I like how you kind of make the analogy to human cognition, because I think in many cases that's the right place to look for inspiration, though not always successfully. So, especially if you look at efficiency, the difference is so ridiculous, right? Like we have these 100 plus billion parameter models. They consume megawatts of energy just for like per hour of inference. I'm not sure what the exact number is. And you have this human brain, which running at top capacity consumes like 100 watts or something like that, right? Uh,
Yeah.
so how do you see like the way forward over the next, if you look a little bit longer, like 5 to 10 years, what are some of the things that we need to be looking at?
Yeah, so it's fun. So we have pretty extreme priors in our intelligence that save us a lot of energy. Like, for example, we have specialized pathways for different types of inputs. You can probably walk and talk much easier than you can walk and read, for example. We also have log scale vision, so it takes a noticeable change for us to register. We don't notice every single change. We also really, one of the most compelling things is that we input a lot of what we see. So we don't need full forward, backward passes for everything. We simulate a lot of what we see. Unless I do something very noticeable, you're likely just infilling me right now. I think that we have some fairly simplistic notions in deep neural networks. So we have global updates, which is a large cause of catastrophic forgetting in deep neural networks. It means that we update everything when we see new data, which it's very hard because it means that we forget initial tasks. We don't have good accumulation of knowledge. That also explains why we have to rely on massive models to learn everything at once. And the adaptation over time is more tricky. We also treat all examples equally, which is fairly naive because I think most people would say not all examples are equal. And I think this is part of the fact that adaptive computation as a whole is it's just fairly hit or miss. So this idea of active learning versus, also coupled with like curriculum learning, is just fairly hit and miss right now. We're not particularly good at it, or certain settings we're good at it, but not others. And so this feels like a very undersaturated direction because we know we ultimately need this for more efficient representations. And so all this to say, I think that a lot of breakthroughs in deep neural networks, but also machine learning as a whole, has been around finding better priors that are more computationally efficient. So convolutional neural networks, a lot of the priors were finally making dimensionality reduction more feasible, right? So you had both convolutional filters, which were very good at parameter sharing and really made it feasible to finally train. But also you had things like, max pooling layers, which reduce dimensionality very, very quickly. So these priors can be quite revolutionary. So I think a lot of it is a combination of priors, which we as humans have. There's certain things we're terrible at because we have heavy priors. Like we're not very well primed for, as I mentioned, walking and talking, but we're also not very well primed for mathematics. Like our brains just don't work in that fashion.
Yeah.
Yeah. And so I think it's figuring out what priors do we impose on models so that it's more efficient for them to learn certain representations.
Still a very large gap. I think it's too many orders of magnitudes to just talk about the priors and the algorithms. Isn't there something like fundamentally wrong with the hardware as well that we're currently using?
You could argue that, but the tricky question is then the immediate follow-up question becomes, well, what else? So this is the hard thing about hardware, is that our search space is very small. So if we think about the development of hardware over time and the available options, we're still in a very narrow search space. So I would definitely suggest there is a very valid question there of compatibility with hardware and also the materials used in hardware. So it's very interesting. Our brain is both hardware and algorithm. It's not like we change our hardware over the course of our lifetimes, but our hardware itself has evolved over the course of many lifetimes. So our intelligence is both structure as well as matter. And I think that you're right. The question is, how flexible is our hardware for different algorithms? The difficulty posed is we don't have a good understanding of the alternative. So we're almost stuck in a local search space there where in many ways, the changes we're making are kind of making it harder and harder to get out of that local search space because you mentioned the new NVIDIA H100, and that's essentially amplifying that trend towards overfitting to a certain type of algorithm.
I guess evolution did something similar to us, maybe, but we're more
Yeah,
lucky in that lottery.
yeah, it's true. It's a valid question. Did we overfit to local minima? Could we be even better? Yeah.
So one of the other topics that you have again and again showed an interest in is trustworthy AI and machine learning, right? And obviously, this is kind of at the bottom of it. It's the fundamental question of when these AI systems gets to be really useful and valuable. How are we going to make sure that we as humans benefit from that, right? That they serve us well in ways that are good for our goals in society and as humans. So what would you say are kind of the top priorities from that point of view in building these large models? Because as we're building these models, they're also become less transparent and more kind of harder to control, right? Than linear regression, say.
Yeah, I think there's a few things. I guess maybe I'll speak to the main challenges for research in this area. So I think one of the main challenges for researchers working in the area of trustworthy ML is to make progress on settings that are more realistic of how models are actually used in the real world. So researchers in the subfield of trustworthy ML often make a few contrived assumptions. So one is that the one typical assumption is that either the bias is known a priori, so you already know what's wrong with your model, and often the assumption is made you have comprehensive metadata for what data is impacted by this bias. So we see this a lot, like in, for example, toxicity. So it's assumed we have a labeled data set of what is toxic. And this is tricky because this frankly is not true of many real world settings. Often you don't really know what your model, what the problematic issue may be. And frankly, you almost never have comprehensive metadata. And often you don't even have data for like a limited subset. So I think that's one area in which we as researchers need to get much better at really this unsupervised setting where you want to surface some parts of the data set that you think might be more problematic based on signals like model signal, or there's more uncertainty there. But this is a more realistic setting in terms of actually surfacing potential issues, not known issues, because we have to remember that notions of what bias is are going to change across countries. So the notion of what is problematic will differ by culture, but also across time. So something that we found funny 10 years ago, maybe now we're like, oh, not so much, So we need ways that are more flexible if we're trying to model a shifting notion of what it means to be harmed. The other thing is what researchers frequently do is they treat it as a static model. So they'll say, for this model, what's the current harm, or what's the measures of harm, and how do we mitigate it? But the truth is, where this is most critical is when you actually deploy a model. So what people care about, if they're truly incentivized about minimizing overall harm, they should care about production systems deployed at scale. But there you have a feedback loop. So your intervention in the system creates this shifting distribution. So there again, we need to have a more realistic notion where we can see how interventions can amplify certain patterns in the data, and where you have measures of distribution shifts so you can evaluate what your impact has been. So these are two really important assumptions that I think we should take to heart in the trustworthy ML research field, where we need to relax the assumption that data exists for everything, because it doesn't, the metadata, that being said, and we need to relax the assumption that it's a static model, because it often isn't. And where we see the compounding of harm is where it's not a static model, and feedback loops do exist.
And so if you look at something like a large language model as a service, in many cases, you wouldn't even necessarily know what the full application is, right? So what are kind of mechanisms that you can build in that make sure that harm is not done?
Well, I think increasingly with the narrative around any model deployed, I think it's really important to have clear audits which are available to people who are using the model. So this is not particular to large language models. This is any model which is deployed. I think this idea of communicating clearly to users what the audit has been to date of what has been verified and the limitations of what has been verified. So this is critical. I also think we need a more nuanced conversation around access in general. So I think we've arrived at a rather simplistic conversation that really we equate responsible with open, but in many ways, like I think we need a more nuanced conversation around how we screen for users and use cases of all models, but particularly ones which will be scaled in different ways. And so there's this interesting narrative, which is, I think we can borrow a lot from essentially security issues in open source software. Like there's this really interesting pattern where in many ways, what we need to have is access for auditing and clear ways in which we can have a broad community provide feedback loops and bugs and bounties. Like I think I am very much interested in this framework and how we could apply it to ML. The difficulty is in security, often it's binary. Is it violated or not?
Right. Yep.
In machine learning, it's a more nuance. So what do we mean when we say undesirable behavior? How does that present? Because it's not an abrupt failure point. It's much more nuanced, and how you validate for that and how you audit it becomes more nuanced. So how would we reimagine things like bug or bounty programs for machine learning? I think this is another interesting direction.
Yeah, it's super. I'm very fascinated by the difference in reception between something which was clearly condemned by everybody, like the 4chan GPT model, which was just very toxic by design, right? And now everybody being very cheerful about stable diffusion, which nobody knows what it can do, and then it can do all kinds of things that you can not even imagine, and everybody was very positive, right?
You've exactly captured, I think, my growing frustration around the lack of nuance in this conversation is that in some ways, so the 4chan model was an interesting, and like it was the end of the spectrum. So people could solidify a more binary opinion around it. But for me, the binary opinion is the issue in some ways, because rarely will we find binary cases like that. But most models will present, in some ways, we shouldn't essentially treat it as good or bad. There's likely a profile of risk for every model. And so how do we get at a more nuanced discussion of that risk profile, rather than now where it's almost treated like a binary, like this is terrible, this is excellent.
Well, one of the issues that plays a really big role in that is that things are just evolving so fast that any sort of, frameworks or legal regulation or even just policymakers are failing to catch up with the latest developments, which brings me a little bit to the end of the interview and something that I have to ask as being from Zeta Alpha, because we work on this. So at Cohere For AI, at Cohere, in your research career, what are kind of, do you agree that this is kind of accelerating to the point of being hardly manageable? And what are some of the tricks and tools that you use for keeping on top of things?
Oh, you mean progress in the field? So in terms of someone being able to keep up with all the innovation that's happened? Okay. Yeah. I would suggest don't try and keep up with it all. I think that to be a generalist in machine learning right now, as a beginner particularly, it's a very painful process. So I would recommend really isolating. I've always said for people, particularly people who are starting out, choose one problem that you think is interesting and work on that. And so we're in a super exciting time in our field because more has happened in many ways over the last 20 years and happened in all of early computer science. So if you think about the 80 years since modern computer science has existed, it's a really exciting time to be involved with the field. And I think part of it is realizing that this is a really exciting moment to get involved, and the rest will come. I mean, I think the biggest revolution is frankly how you can be involved. You used to have to go into a fairly narrow set of spaces in order to be involved in this type of research and progress. Now it's completely different. I mean, we're changing the spaces in which research can be done and where, how, and by whom it can be done. So this for me is one of the most fundamental revolutions, is that the notion of progress and who can participate is totally different. So in that way, people are very lucky to join now, because even 10 years ago it would have been a far more narrow, contrived process to be able to contribute. And now you can start contributing really immediately. You can join a community research group. You can start getting involved. My main suggestion is narrow your focus. Otherwise,
Right. So
um,
you do think that a little bit like in the life sciences, we'll get this sort of fragmentation of specializations, that you're an expert on like the mitochondrial DNA, but you have not so much about the general.
It's slightly different. So I would say one thing. As a beginner, I think it's always important to narrow focus. As a career, I think it's always important to dabble. So I do think that if your career, if this is what you're going to do, you should touch multiple subfields because it makes the best researchers. It's very hard to unlock new directions if you stick with one area only. We have seen the industrialization of science, but there's typically two different stages. So one is the breakthrough, and that requires someone who is connecting ideas in new ways that haven't been done previously. The other is the exploitation stage. So industrialization of science works very well for the exploitation stage, but the breakthrough still requires, I would say, the explorer type mentality where you're able to dabble and able to see things that other people haven't.
And so my last question is, do you think AI will help us with how we perform science and kind of explore new fields of knowledge?
I really do think so. I mean, part of what I think is exciting about our current set of models is that there's differences in performance. We often hold the human benchmark as the gold standard, but it's not quite clear to me that's true. One of the things I like about when AlphaGo came out is that Go players would really enjoy playing against AlphaGo because it would teach them new things about the game. And I think in many ways, there's some things that we're clearly not very good at parsing in science, right? Where I've seen super exciting developments is even in materials design. So if we think about things like plastic that's actually recyclable, or if we think about things where we try and change the materials available to us, that combination of trying to estimate what materials go where and how we can develop new materials, that's where AI has a natural advantage. We don't parse interdependent variables very well. We can't quite quantify. So I think this is where when I work a lot in interpretability, and often people who work in interpretability say, oh, it has to adhere to what a human would do in the situation. I actually strongly disagree. I think part of what a good interpretability tool should do is highlight difference without suggesting that you have to anchor to human performance, because it's often the differences that we learn something about the task. And that's where I think it can really aid in scientific endeavors, is illustrating a slightly different function to get that mapping of our problem space.
Diversity of ideas is important, and I'm looking forward also to see how with Cohere for AI, with that as one of your guiding principles, you're gonna contribute to shaping the future of our field. So thanks for the interview, and
lovely chatting. Thank you so much for the invitation. This was really, really fun.